Now we will go to the second lecture of week 2 of this course. In this lecture, I will be talking about a little bit more about unit cells. I will be talking about what is a conventional unit cell and what is a primitive unit cell. So, as we saw in the last class, a unit cell is a repeating unit of the crystal. So, now let us talk about what is a conventional unit cell and what is a primitive unit cell. So, as we saw in the last class, a crystalline solid consists of some repeating unit, and that repeating unit roughly we called it the unit cell. And what we said is that this unit cell is the repeating unit of the crystal, and translations of the unit cell have to fill the entire space without voids. And this was very important. We said that the translations of the unit cell should fill the entire space without any voids. Further, we said that the unit cell is chosen to have the symmetry of the crystal, and we also saw that the choice of the unit cell is not unique. What we mean by that is there are several choices for unit cells. And at the end we saw that you can define the unit cell using 3 lengths and 3 angles. So, this was what we learnt in the last class. Now, let us talk now about what is a primitive unit cell. So, now in order to understand a primitive unit cell, you really need to think of the repeating units as either atoms or molecules. So, a unit cell that contains exactly one atom or molecule is called a primitive unit cell, and I have sort of gone a little ahead of what we are discussing now, in the sense that that we should keep in mind that when we refer to a crystal, it is composed of both a lattice and a basis, and we will come to this a little later, but let us just try to go ahead with this unit cell. So notice that if you take the FCC or BCC unit cells, they contain more than one point. So many of you, all of you would have heard of an FCC, which is actually a lattice. So if you had a face centered cube, then we would think that there are these points, which could be atoms if it is an FCC crystal, and we say that these points are also located at the face centers. And so this is an FCC. Whereas a BCC will look exactly like this. Only thing, there is one additional point at the body center. So, now the BCC, as you are aware, this contains 2 points, and I am deliberately leaving it at points. I am just calling these points as opposed to atoms or molecules, and this distinction will become clear as we go along, and this contains 4 points. And let me emphasize what you have already learnt in your high school, that each of the corner points contributes 1/8 to this unit cell. So, you have 8 corner points. So, the total you have effectively 1 point per corner atom, and then each of these face center, each of the 6 face centers contributes half. So, you have 6 into half, that is 3. So, you have 3 plus 1, 4 points. And here in this case you have you have one from the corner and one from the body center. So, you have 2 points. Okay. So, what you see is that if you choose this as the unit cell for FCC, then you will have 4 points. Similarly, if you choose this cube as the unit cell for BCC, you will have 2 points. Okay. So, does that mean that if you have an FCC or a BCC, you cannot have a primitive cell? And the answer is no. It is possible to define primitive unit cells that contain exactly 1 point in FCC and BCC. Okay. Now, let us just step back and say again that if you take this unit cell of FCC and you translate it in all directions, you will get the entire crystal and you will not have any voids. Similarly, if you take this BCC unit cell and you translate it in all directions, you will get a crystal without any voids. However, both these unit cells have more than 1 point. FCC has 4 points, BCC has 2 points. So, these are not primitive cells. Okay. So, these are not primitive, not primitive cells. Okay. Notice that it is the cells, it is the unit cells that are not primitive. Okay. Now, so the question is, can we suppose you have an FCC lattice, is it possible to define a unit cell for an FCC lattice that has exactly 1 point? And the answer is yes. The answer is that there is a construction called a Wigner seat cell, okay, that allows you to construct a primitive unit cell for any lattice. Okay. So, and this Wigner seat cell is a unit cell that contains exactly one atom or molecule, and it has all the symmetries of the crystal. So, I will just illustrate what a Wigner seat cell is. Okay. And let us take an example. Okay. Again we will start with 2D example of how to construct a Wigner seat cell. So, here I have a 2D, this is a 2D lattice, it is referred to as a centered rectangular lattice. I emphasize that I have not really discussed lattices in detail, but just take this as a given that this is a centered rectangular lattice. And you can easily see that if you choose a unit cell, you can easily see that you can choose this yellow shaded region as a unit cell, and this unit cell will contain 2 points. This contains 2 points. Probably yellow is not very visible. Let me use a different color to show this. So, this cell contains 2 points. So, this shaded yellow cell, it contains 2 points per unit cell, and how did we get 2? Because each of these, this is a 2-dimensional lattice. So, each of these they contribute to this atom right here. Okay. It contributes to four cells, it is a part of 4 cells. Okay. It is a part of this cell, this cell, this cell, and this cell. So, to this unit cell it contributes 1/4, and so each of these contributes 1/4. So, you have a total of 1 atom due to this, and then you have 1 atom which is entirely inside the cell. So, you have 2 points or atoms, if these were atoms, okay, per unit cell in this yellow cell. So, now let us construct a Wigner seat cell. Okay. So, how will we construct a Wigner seat cell? So, the way to construct a Wigner seat cell, okay, is to choose a, so we will start. The first step is to choose an atom or an atom. Okay, I should not use atom, I should really say choose a point, because these are what we have considered here are just points. Okay. And look at nearest neighbors. Okay. So, NN stands for nearest neighbors. so if I choose, let us say I choose this point, okay, and I identify its nearest neighbors. Let me identify it in light blue. So, the points nearest to this are this, this, this and this. Okay, it depends. I mean, if it depends on whether this length is longer or this length is longer. Okay, but let us and that really depends on the dimensions of the rectangle. Okay, so let us consider a case where these lengths are the shortest. Okay, then what you do is you draw this line from here to here, and so you consider this line and you bisect it. So, you bisect it, okay, you cut it in half and draw a line perpendicular to this line. So, let me draw it this way. Okay. Similarly, I draw a line perpendicular to this line. I draw a line perpendicular to this line, and finally, I draw a line that is perpendicular to this line. Okay. So, these are lines that are perpendicular to each of these lines that join the nearest neighbors. Okay. So, the second step I should write is to draw perpendicular lines bisecting segments. Okay. And what I mean when I say segments, what I mean is bisecting these segments that join the atom, that join the point to its nearest neighbor point. Okay. Next, what do we do? Next, you consider next to nearest neighbors and repeat. Okay. So, in this case, let me mark the next to nearest neighbors. I will choose a different color. So, the next to nearest neighbors are this and this. These two are the next to nearest neighbors. Okay. And if I draw lines bisecting them, then I will get so I will get something like this, and I will get a line that looks like. And as the procedure goes, you are supposed to continue, okay, but we already see that so repeat and then choose common area. Okay. Now you can already see that if you just take the nearest and next to nearest neighbors, okay, so the common area, okay, let me mark it in green. So, this represents the common area. Okay. Now, the question is, should you go to more cells, more nearest neighbors? So, if you go to this nearest neighbor, so for example, if you go to the third nearest neighbor, okay, you can easily see that it will not contribute anything else. Okay. So, let me take this orange color for the third nearest neighbor. So, the third nearest neighbor is these points, and you can see that the bisector, okay, comes here, and the common area of the three regions is still this. Okay. So, you need to go, in this case you need to go only up to the second nearest neighbor. In some cases you have to go to more nearest neighbors, okay, to get the common intersection area. Okay. What I want to emphasize is that this region in green, okay, it is formed by the intersection of all these segments corresponding to the nearest neighbor, to successive neighbor points. Okay. So, this is the basic construction of a Wigner seed cell. Okay. And you can do this for any lattice. Okay. So, what do we get at the end? So, at the end you get this, this is your primitive cell, okay, and this contains exactly one point, as you can see, and it turns out that it has all the symmetries of the crystal. Okay. It's actually, it looks like a regular hexagon, but it's not actually a regular hexagon. It's a slight, I mean, whether it's regular or not depends on the exact dimensions of the rectangle. Okay, but it is not meant to be a regular hexagon. Okay, and what is more is that it contains all the symmetries of the crystal, and you can see that by translating it, you can form the entire crystal without any voids. Okay. So you have to consider translation vectors. Okay. So for example, if you translate along these two directions, you can easily generate the entire crystal without any voids. Okay. So this is the idea of the Wigner seed cell. Now it turns out that you can do this for an FCC. You can take an FCC in 3 dimensions and you can do this. Okay. Now this is considerably harder to visualize. Okay, because in 3 dimensions you will not have perpendicular lines as in 2D. Okay, so this perpendicular, you will have a plane that is perpendicular to each segment that connects a point from its neighbor. So and here you have in 3D. So I will just mention this, that in 3D you have planes of intersection. Planes intersecting. So instead of having lines, okay, instead of having lines intersecting, you will have planes that are intersecting. Okay. So for example, if you had an FCC, okay, let's say you had a So if you had a face centered cubic lattice, okay, then if you take any point, okay, so let us say you take this point in red, okay, and you look at its nearest neighbors, okay, it will actually have a total of 12 nearest neighbors. Okay, so the 12 will be this, this, okay, and then so these 4 will be in this unit cell. Then there will be 4 more in another unit cell. So I can just show. So in this neighboring unit cell there will be a point here. Okay, there will be a point in this the cell that comes out in this direction. There will be another point. Okay, here. So essentially, if I take this out and I show it, so I'll have a point like this, and I'll have nearest neighbors. I'll have 4 in the perpendicular direction, 4 in this direction, okay. So I have 4 this way. Okay. And you will have 4 more in the third plane that is perpendicular to these two. Okay. So and that will be the plane of this paper. So you will have 4 in this direction. Okay. So you will have a total of 12 nearest neighbors. Okay. And you are aware that the coordination number of FCC is 12. So these are the remaining 4. Okay. So there are 12 nearest neighbors, and now if you imagine that you are dropping segments to the nearest neighbors. Now what is perpendicular to this will be a plane. Okay. So the object that is perpendicular to this will be a plane that goes in this direction, and it is perpendicular to this line. So you will have planes intersecting, and now you can see that it's a lot of work to actually find out the Wigner seed cell. I mean, you need to draw bigger cells and see what is the plane of intersection. But again this can be done with a lot of effort, and what you will find is that the Wigner-Seitz cell for FCC is a rhombic dodecahedron. The Wigner-Seitz cell for BCC is a truncated octahedron. Okay, so these actually can be, you can do these. Okay, so this rhombic dodecahedron has exactly one lattice point, okay, per rhombic dodecahedron, and it has all the symmetries of the FCC lattice. Okay, so the idea of Wigner-Seitz cell is very useful. Okay, we won't actually be working so much with Wigner-Seitz cell, but it is very useful to know that there is something called a Wigner-Seitz cell, and this information that you can always find a primitive cell that contains exactly one point and that has all the symmetries of the crystal is very useful information. Okay. However, when we are dealing with unit cells for FCC, or BCC, we will use the conventional cell. So, the conventional unit cell is a cube, and for FCC it has 4 atoms, 4 points per unit cell. For BCC it has 2 points per unit cell. Okay. So, I will conclude this discussion on unit cells here, and in the next lecture what I would like to do is to talk about lattices more formally. Okay. So, we have been talking about lattices in this lecture, okay, but we have been talking about it informally. Okay. In the next lecture I will formally introduce the lattice and what are the different kinds of lattices. Thank you.